Sorry, just technical. Okay, just technical things. But anyways, I guess I'll say that again for the recording. But I have a form, and thank you to the person who filled it out. Okay. Anyways, let's get started. So I did this last week. Okay. So this week we're going to be covering a lot about the solar system. Waiting for it to load. I was saying this as people were, filing in, but today's lecture is going to be just a lot of data. It might be a little bit boring, but we're talking about the solar system, which is a really important part of astronomy, and I wanted to cover a lot about this particular topic today. So, anyways, I guess first to the people who are here, how was your week? If you want to put an emoji in the chat. I can't see the chat at the moment, but I can definitely check it out after the meeting and maybe talk with you guys at the end of class. So anyways, I'm a little bit, low-key day today, but I'm excited to be here. Okay, anyways, so today we're going to be covering, starting with the sun, the object at the center of our solar system. We're going to do a really in-depth thing about stars and star formation. I think it's starting the week after next, so I'm not going to go as in-depth today as I normally would, but I'm just going to talk about a little bit about the specifics of our sun and how it affects like the solar system as a whole. I'm also going to talk a lot about the moon because it's really important, and it's also one of the closest objects and like most observable objects that we can see. Obviously the Earth, because it's a very important part of our solar system. And then I'm going to go over just like I said, the statistics a lot of each of the planets and what their like unique attributes are and like their specific roles in the solar system, and then also other objects like asteroids, comets, meteors, dwarf planets. The difference between like shooting stars and meteors and meteorites. It's like, I don't know. I feel like that's like a contentious topic, and we're going to talk about it. Also, I'm going to talk a little bit about human exploration because that's one of the things that people like to talk about a lot with astronomy. It's pretty important, and we're going to get into a lot of that. Okay, so first of all, starting off, this is a to scale sort of model of the solar system. So not to scale in terms of like distance, but to scale in terms of like the size the relative size of the planets in the entire solar system. I think this is like a really cool, can I get my little clicky thingy? Okay, yeah. This is a really cool, I guess, model of the solar system. So with the sun, we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And then I guess that's Pluto. It's very tiny. And we'll talk about that in a minute. So anyways, as you can see, Jupiter is gigantic, and then the sun is even bigger. And in comparison to all of that, there's us. So anyways, I think I have a distance scale model later in the slideshow. But anyways, the first thing we're going to get into is the sun, which is the start of our entire, I guess, reason we're here. Whoa. Okay, so the sun formed about 4.6 billion years ago. Here's a little image of what it might have looked like while it was forming. This is called a protostar. It's a bunch of gases orbiting each other. Eventually they condense, and then a star is born. So the sun is, of course, a star. And like I was just saying, it was formed because of a supernova that released a bunch of energy and sparked a cloud of dust to start condensing. You might have heard the expression that we're all made of stardust, and this is very true. Yes, like I said a few minutes ago, I'll definitely be getting a lot into star formation later. It's a little bit tedious, but it's also really interesting, and it's a really important part of astronomy. So if you measure out the number of atoms, not the mass, but the number of atoms, the sun is 92% hydrogen, which is a little bit crazy, and 7.1% helium. So if you know anything about chemistry, those are the first two elements on the periodic table. They're like the simplest, and this is why they're the most abundant. When the star does nuclear fusion, which we'll talk about. It takes hydrogen atoms, which are the simplest, and condenses them and makes them into helium and all the other elements. But the sun is, relative to other stars, a kind of new star. So that's why it doesn't have that many other elements in comparison to its like majority hydrogen and helium. So inside the sun, it's less than 2% other elements, and the sun makes up 99% of the matter in the solar system, which is why if we look at like the composition of the solar system as a whole, even though it's really big, most of it is empty space, and the actual matter in it still only makes up 0.2% of the matter other than the sun. So 91% of the solar system is hydrogen, 9.8% is helium, and it's an even smaller percentage, 0.2%, is all other elements. So everything on Earth, almost everything on Earth, everything on Mars, almost everything, on the rockier planets is only makes up about 0.2% of all the other elements in the solar system compared to hydrogen and helium. So I think these are the correct numbers. But anyways, that's kind of crazy. So everything, like all life, sorry, I'm stressing this, but all life only makes up 0.2% of the matter in the solar system. And a fun fact is, I guess, that because of the abundance of hydrogen and helium in the universe as a whole relative to all other elements, anything other than hydrogen and helium, not we, but astronomers, I guess, or actually no, we can say we because we are being astronomers. But anyways, we sometimes call everything other than hydrogen and helium metal, which is kind of crazy if you think about it, because I have a pencil here. We don't think of this as metal, but because of how little other matter there is, it's metal, I guess. Anyways, that's just a fun fact. So the structure of the sun is really complex. It's about almost 500,000 miles, or almost 700,000 kilometers in the radius. So just this little part here is that much. So if all the way across, it would be a million miles basically, which wow. And so the sun is made out of, because it's so big and it's so because it's so big, the force of gravity puts a lot of pressure on the inside part of the sun, and that makes it really hot. And because it's really hot, and heat is also a measure of energy, so because it has so much energy, the atoms in it turn into plasma, which is a little bit complicated to explain, but it basically means that atoms, you have your nucleus with protons and neutrons, and then your electrons orbiting it. You might have learned that in science class a tiny bit. If not, that's totally fine. But the electrons that I mentioned that are orbiting the atom, they split off and they kind of just float around away from the atom that they were connected to. And this is really weird because normally matter doesn't exist in that kind of state, but because it's so hot in the sun, it exists as plasma. And this is what allows nuclear fusion to happen, and for, like I was saying a minute ago, the sun to create entirely new elements in its core. We'll definitely get more into that later. But the sun has a few layers. The core, where the nuclear fusion happens, the radiative zone, the convection zone. You might have learned about convection also in your science class. It's when things move around, specifically things in liquid form move around, or gas form. Anything that's not in solid form, basically, move around. Sorry, got sidetracked. And they disperse energy and just move things around. Yeah, okay, so that would be this inner stuff. And then the outer stuff is the photosphere, chromosphere, transition region, and corona. I'll be honest, I don't know that much about this, but I do know that the corona, compared to the heat of the surface of the sun, is what is that? 20? No, I think that's 2,000. Yeah, that's 200. I don't know. I think it's 200 or 2,000 times hotter than the surface of the sun, which is weird because the corona is on the outside of the sun. So you would think that it's not as hot as the center of the sun, because the center of the sun is where all the heat is being generated and it radiates out. and you would expect it to lose heat as it goes outward. But for whatever reason, people aren't entirely sure. They think it's because of like electromagnetism. So like electric current and magnetic current like interfering and like releasing more energy as it leaves the sun. They think that that's why it's hotter on the outside of the sun than the inside. That's one theory that's pretty strong, but people aren't entirely sure. But anyways, this is what the corona looks like when you can see it during a solar eclipse. Like, you know, the sun and the moon are pretty much the exact same size in the sky, which is a coincidence, but it's pretty cool. So when there's a solar eclipse, the moon goes in front of the sun and you can see the corona, which is really cool. It's like the layer that's like radiating outwards. Anyways, so the sun, as we probably know, is a very big part of our solar system. So it creates new elements in its core through nuclear fusion. I think I explained this, but basically because the sun is so big and it has so much mass, it creates like its own gravity. And this builds a lot of pressure in the center of the sun, which builds energy, and hydrogen breaks apart and forms helium. And then this process happens a bunch of times, and eventually you get you go along the periodic table and you get new elements. And at the end of, if you have a really big star, it can generate up to iron. We'll get into that. But yeah, a lot of elements are formed in the center of stars, which is really cool. The sun also emits electromagnetic radiation, and this goes all across our solar system. It's the reason why we have life on Earth. And even if you were millions and millions of miles away, if you looked hard enough, you could see the sun, which is pretty cool. Yeah, so because of the nuclear fusion in the center of the sun, energy is emitted in the form of light. And it emits, if you see over here, all kinds of light on the electromagnetic spectrum. I'll explain that at some point, sorry, but basically light is a form of like, I don't know how to describe this exactly, but light, if it has more energy to it, you aren't able to see it. And if it has less energy to it than like visible light, you also aren't able to see it, but it's still a form of light. And the sun, as you can see, mainly emits visible light. And this is why probably evolutionarily we like evolved to be able to see visible light, because the sun mainly emits that, which is a kind of interesting fact. Anyways, I'll probably explain that more later, but the sun also has an active magnetic field, which is caused by the electrical currents and the movement of particles within the sun. So the magnetic field actually flips every, I think, 11 years, I'm pretty sure. And this can be really dangerous when it happens because a lot of electricity and a lot of like magnetic fields like get splashed all over basically. This is called, and also like particles that, as we mentioned earlier, have a lot of energy. Something on my wall, sorry. They get like ejected and they can actually come and hit the earth. And this is very dangerous. So this, something that happens like a lot of the time, not all of the time, but a lot of the time, is that these like particles from the sun travel towards the earth. And the earth actually has a magnetic field, and most of the time the earth can like fend off the particles. But it's a magnetic field, and if you know, magnets have two poles. So I don't have a good I don't have a good image right now, but at the top and bottom of the two, at like the North Pole and the South Pole on the Earth, the magnetic field kind of like stops, or like it goes into the Earth. And at these 2 points, you can see the northern lights. This is caused by, like I said, the particles like reaching the like kind of weak point at the top of the Earth and traveling into the atmosphere and causing all sorts of interactions with particles in the atmosphere. So yeah, basically particles from the sun travel all the way to the Earth, get around the Earth's magnetic field, and cause the northern lights, which is really cool. But I was talking about coronal mass ejections a minute ago, which, like I said, can be dangerous. And this is because sometimes the magnetic field of the sun is so strong that it can like merge with and mess with the magnetic field of the Earth. And this can cause the Earth to not be able to deflect these kinds of particles that are coming from the sun, they're highly energetic particles. Oh, they're highly energetic particles, and they can sometimes mess with like electronics. So you might have heard something about this, like a solar storm, where you have to like turn off all sorts of electricity, or else it'll like kind of get messed with, which can be really dangerous. I didn't do a great job of explaining that, but you should definitely look into it if you want to learn more. It can be a little concerning, but also there's a very low probability of this like actually hurting us in any big way if we take like preventative measures. Anyways, so the sun is 93.7 million miles away from the Earth, which we like in astronomy define as one astronomical unit, which makes sense. So if you see any kind of measurement with 1 AU, if it's like some object is 6 AU away from the Earth, that means it's 6 times the length, 6 times the distance that the Earth is from the sun. So very far away if it was 6, but that's a pretty helpful measurement. And light has a specific speed that it can't go over. So that means that in 8.19 minutes, light can travel 1 astronomical unit, or functionally, that definitely light, it takes light 8.19 minutes to travel from the sun to Earth. So like the sun has facilitated life on Earth. It heats the planet, it causes seasons and photosynthesis. It plays a pretty big role in the tides. That's not just the moon. It provides us with energy and so much more. Basically, life would not be possible whatsoever on Earth without the sun. It just so happens that the Earth was in the exact right like position relative to the sun, the exact right like size. The sun is the exact right size. So many different things lined up. It was such like a play. It was such like a crazy. What do you call it? Like it was such luck that we are here, but at the same time, we wouldn't be here unless all of those cards had aligned. So yeah, another pretty crazy thing, but it's all thanks to the sun. Oh, and yeah, this is what I was trying to explain, but high energy particles can like get around the magnetic field, the protective magnetic field of the Earth, and they cause the northern lights or the aurora borealis. Okay, anyways, onto the moon. So the moon formed, if you remember, the sun formed 4.6 billion years ago. The moon formed, so 100,000 years after that. So it's 4.5 billion years old, or 100 million years younger than the solar system. It most likely formed, if you see this little, what do you call it, diagram, the moon most likely formed when, I guess, Theia collided with Earth. Earth was still in like a totally rocky form at this point, no water, no like trees, no life, but most likely an impact happened. And that means at one point, the Earth had like a disk around it, kind of like what we see with Saturn, which is pretty cool to think about. And eventually that like disk of debris formed with like gravity and stuff and formed into the moon. So another interesting fact is that when the Earth and the moon formed, a day was only 4 hours long. So that means that initially the Earth was rotating around itself like at a much faster rate than it is now. But because of the moon's like pull on the Earth, like the Earth pulls on the moon, but the moon also pulls like back a tiny bit on the Earth. This caused the Earth to stop rotating as fast as it normally does. So a day, over the last 4.5 billion years, a day has shortened from 4 hours to 24 hours. Just nice. Ooh. Anyways, sorry, you can't really see that, but it says function up here, and the moon has a lunar cycle. So we all know, like, you know, the moon orbits around the Earth every 28 days. It goes through a bunch of phases. It's a new moon when, if we have the sun and we have the Earth, then when it's new moon when the moon is in between the sun and the Earth. So all the light from the sun is hitting the back side of the moon that we can't see, and this is why the moon appears like completely dark in the sky. And then sorry. And then when the moon is on the opposite side of the Earth from the sun, it's completely bright because all of the light that's shining on the moon is shining on the visible side to us. So if you think about it, the moon is always half lit up by the sun, but it's only that we can only see like a specific like fraction of that half lit up moon as it goes through the phases, and this is what causes the phases. So you can see like it's half lit up, but the side that's facing us is dark. The side that's facing the sun is light. It's a new moon. When it's half and half, in line with the Earth, you can see half and half. And when it's all the way on the opposite side of the sun from the Earth, it's totally full. You can just study that a little bit, and it makes sense. And the moon orbits counterclockwise, and it also the Earth also orbits or rotates counterclockwise, which is a fun fact. They're like synced up. I'll talk about that in a minute, actually. So yeah, the moon goes through its whole cycle roughly 13 times per year. So its period is about 28 days. The moon, like I was saying a second ago, also rotates, but weirdly enough, its rotation is synchronized with this orbit of the Earth. So because of its formation and all of that, for whatever reason, the moon has formed so that we only see one side of it, like ever. One side of the moon is only ever facing the Earth. I don't know why, but that's something that I never really realized until I started looking into this stuff. So yeah, like I was saying a second ago, the phases of the moon are caused by the angle at which light from the sun, like the angle at which that light reaches the Earth. So then it causes like different portions of the moon to be lit up for us, even though half of the moon is always lit up at the same time. Another thing that's kind of weird is that the moon appears in different places in the sky at different times throughout the month. If you think about it a little, okay, wait. I've tried to explain this multiple times, but I've never been very concise, so I might come back to this part because I'm running a little bit slow. But if you've ever thought about it, like you don't really see a full moon in the sky ever, and that's because when a full moon is in the sky, it's because the moon is on the opposite side of the Earth to the sun. So when the Earth is facing the sun and it's daytime, the full moon is on like the exact opposite side of the Earth to the sun. So you're never going to see it. But if you look really hard in the sky when there's a new moon, you can see it sometimes because the new moon is going to be on the same side of the Earth as the sun. So it's going to be out during the daytime. And then if we have a half moon, it's going to be visible from about noon to midnight because the Earth is rotating clockwise, if you watch my little thingy. And when it's noon and the Earth is like directly like in line with the sun, kind of, the half moon is like visible on the horizon, and then you go to 6 p.m. and then the moon is like directly above the Earth, and then you go to midnight and it's on the other horizon. Sorry, I don't know if I explained that very well. It's totally fine if you don't get what I'm saying. But just remember that the moon like is in different places throughout the sky throughout the month, depending on its phase. Anyways, the moon also keeps the tilt of the Earth stable. I talked about this last week, but one of the reasons why the zodiac isn't entirely accurate is because the Earth's rotational axis has been like tilting throughout the years. So one of the things that keeps the axis from going like all out of whack is the fact that the moon is pulling on the Earth and it's stabilizing it. So like I said here, without the moon, the Earth might have crazy seasons because the axis might be like really, really tilted. And when you're in the summer, like one side of the Earth or like one part of the Earth would always be getting sunlight. It would be really hot down there, and then in the winter it would like never be getting sunlight. It would be really cold. So the moon helps the Earth's axis of rotation like remain stable, and it regulates the seasons a little bit. Anyways, so as we've all heard, the moon affects the tides on the Earth. Because the Earth is pulling on the moon to keep it rotating around it at all times, but because of the laws of gravity, the moon is also pulling on the Earth a little bit. So, things like it's not that strong of a pull. So things like there's a tree outside my window. Things like trees, houses, us aren't going to be pulled up towards the moon because the gravity isn't strong enough. But things like water are pretty like malleable and they can easily be pulled. So this is what causes like the water to rise during high tides and go down during low tides. It's just like going towards the moon. And then this also happens with the sun. And if you've studied the tides a little bit, you might realize that the tides also fluctuate throughout the month. And this is because like of the alignment of the sun and the moon lining up sometimes. So I don't know how to explain this that well, but when they're in line with each other, it causes a really, really strong high tide, and then maybe like not like a really strong high tide, and then maybe a really low tide. And then when they're opposite each other, the low tide and the high tide kind of cancel out, so it's not as extreme. Anyways, basically tides can tides change throughout the month. So also eclipses happen, which because the sun and the moon are at the same size in the sky, the sun can the moon can perfectly block out the sun and cause an eclipse, which we see up here, and we can also see the sun's corona. It looks like an eyeball, which is pretty cool. And eclipses have long been part of like people like think try to think up meanings for them, have symbolisms, all that. It's pretty important cultural phenomenon. The moon also provides light for us at night. We wouldn't be able to get things done. Nocturnal animals have evolved to use the moon's light at night, and otherwise this wouldn't really be able to happen. It's a useful tool for navigation sometimes. So if you were a sailor, you would have had tools that I was talking about last week, like the astrolabe, star charts, but you can also use the moon. I don't know how that works, but if you know a lot about like where things are in the sky because you relied on them rather than GPS, you would be able to find your way using specifically the moon. Of course, the moon has always been a subject of human interest. And I was talking about this last week, but India has recently sent up a mission to the moon to look for frozen water and a possible sign of life. So in the future, this might be important for us and something that we should probably pay attention to a lot right now. Okay, we're getting onto the Earth. So the Earth formed at around the same time as the moon, about 4.5 billion years ago. And the Earth is mostly made out of nickel and iron. If we see up here, when the Earth first formed, it was mostly like it was really hot. There wasn't any water. Things were still moving around like crazy. It's basically one gigantic volcano. And as we can see, the moon, this is the moon. It was a lot closer to the Earth than it is now. As things have like happened, the moon has slowly like drifted away from the Earth, but it's still here and it's still really important. But when it first formed, it was really close to us. Okay, so it's mostly made out of nickel and iron, which are elements that can be formed in the center of stars. So if you remember what I said earlier, the entire solar system, but specifically the sun, was made out of, or was like caused sort of by a supernova, so the explosion of a star. So all of the elements that we have now up to iron were like formed during inside of stars. So the Earth is very much stardust. But anyways, initially, like I said, the Earth was mostly rocks, and eventually it cooled down enough for things to happen. And one of the things that happened was that water had like been arriving on Earth over the years on asteroids, and initially it was like too hot, but water had like evaporated and condensed a little bit, and eventually it condensed into oceans. Initially, also, the Earth didn't have an atmosphere, but an atmosphere forming was what allowed any water to stay present on Earth and for any life to form. About life forming. So, Earth is in the exact right zone for life to form. So, it's enough away from the sun that any water can like stay in a stable state, but it's also far enough away, or it's like far enough for any water to not evaporate, but it's also close enough for any water to stay in a liquid state. And I'm talking about water specifically because water is very important to the formation of life. Biology lesson, I guess. But water has a bunch of weird properties that allow life to form. Like it can bond to itself. It can make uh, a weird layer on the top of itself and like it sticks together. It freezes in a less dense, like it freezes and turns into a solid, and it's less dense than it is in a liquid, which is really like atypical for any substance whatsoever. And there's a bunch more weird properties, but basically the takeaway is that water completely necessary for life to form, and Earth happens to be in the right zone for water to be able to exist in all three states and work for us. So Earth's atmosphere is also incredibly important. It blocks out deadly radiation from the sun. Like I was saying, light, the electromagnetic electromagnetic spectrum, has a bunch of different levels of energy that it can be, and energy levels that are like higher energy than visible light can be really dangerous to us. So the sun does emit those levels of light just in lower quantities, but our atmosphere works by reflecting off light and also letting out light that's radiated by the Earth's surface. And overall, it protects us, but it also keeps in like it keeps in energy that we do need to keep our planet warm enough. So that the atmosphere is really important. Also, global warming has been happening recently. So carbon dioxide has been thickening the atmosphere and not allowing as much light out, which is why energy in the form of heat has been building in the atmosphere and why our Earth planet is getting warmer. Anyway, that is a thing. I think I have a slide about it. I don't have a slide about it. Never mind. That's an important thing that is happening to the atmosphere. Anyways, water is a really important part of life, and Earth has plenty of it. And the sun and moon have both, in their own ways, allowed for the formation of life, with the tides being changed and animals evolving to night and day, and all the different intricate systems that have formed on the Earth because of the presence of the sun and the moon. Okay, I might talk about this stuff a little bit later if I have time, but right now I'm going to move on to the planets, which are a little bit more interesting to us, maybe. So a lot of this is just going to be statistics. I'm sorry, but I hope you guys enjoy it. So anyways, Mercury, which is the closest planet to the sun, is pretty. But it also has a period of orbit of 88 days. So it orbits around the sun every 88 days because it's very close to the sun. As we can see over here, it only has it only has a distance from the sun of 0.4 times the distance of the Earth to the sun, so a lot closer. It's also 1/3 the size of the Earth, which is, yeah. Temperature, it's very cold. So it's from negative, negative 173 degrees Celsius to 427 degrees Celsius. I didn't write Fahrenheit on here, sorry, but that's a pretty big variation in temperature. I didn't put down a rotational like duration, but basically I'm pretty sure its days are a lot. I'm not sure actually, but it definitely has a different length of like rotation, so a different like length of day than the Earth does. And because of this, one side of Mercury that is facing the sun is a lot hotter, so it's 427 degrees Celsius, which is very hot. And then the back of it is very cold, which is negative almost 200 degrees Celsius, because it's not facing the sun, and also because it's so close to the sun, and that's why it gets so hot. It's mostly made up of iron, which is one of the elements that can form in the center of a star. Because it's so hot and close to the sun, it has a liquid iron core. In order for a metal to be liquid, that means it's very hot. So it doesn't have a thin atmosphere, which means it isn't conductive for life. And in terms of like being a human, if you want to see it, because it's close to the sun, you can only see it during sunset and sunrise, because otherwise you would have to be looking into the sun, and the sun is so bright that you can't see any sort of planets near it. But you also wouldn't be able to see it at night, because it's on the, like, if we're looking out from the Earth towards the stars, Mercury is on the other side during the nighttime because it's near the sun. But anyways, if you want to look for it, it's in the west in the evening, because the sun rises in the east, sets in the west, which means that Mercury also rises in the east and sets in the west. So if you want to look for it near the sun, either after the sun has set, but like Mercury is still there, or before the sun rises, so that the sun doesn't block out the light. Anyways, on to Venus. This is the very hot planet. So its period of orbit is about 225 days. The distance from the sun is 0.7 astronomical units, and it's roughly the same size as Earth. However, because it says down here, because of its very thick carbon dioxide atmosphere and also sulfuric acid atmosphere, if you've heard anything about greenhouse gases, you know that they trap heat in because of like how they interact with light and energy coming into the atmosphere. This means that Venus is very, very hot, and also that it's like roughly the same temperature around the entire planet, no matter what side is facing the sun. But it's carbon dioxide is an insulator, so this makes Venus very hot, even though it isn't the closest planet to the sun. It's still the hottest, which is something that you can remember it by. It's also mostly made of iron. It has a solid iron core. I don't know why, but it does. And yeah, it's very hot. It looks a little bit like Mars, but it's different. Anyways, it's very bright in the sky compared to Mercury. Like, really bright. If it's in the sky during that day, you'll definitely be able to see it. And because it's one of the planets that's near the sun, like relative to the Earth, it's going to be in the same like location and time roughly as Mercury is. So it's going to be to the west of you during sunset, and to the east of you during sunrise. Yeah, it's very bright and very hot. Okay, moving on to the Earth. The period of Earth's orbit, as we know, is 365 and a quarter days. It's 1 astronomical unit from the sun, and the Earth's radius is like 4,000 miles, or 6,300 kilometers. So on average, about 57 degrees Celsius, and it's mostly made of iron, oxygen, silicon, and magnesium. I'm talking about like specifically in its core, but of course the Earth has many, many more different elements that we all use and interact with a lot of the time. So the Earth's surface is mostly water, the oceans. This helps regulate the temperature a little bit. We also have an atmosphere, and our atmosphere is, weirdly enough, 78% nitrogen and 21% oxygen. But still, this atmosphere is very conductive for life. Anyway, I was saying a minute ago, but there are so many different cards that we metaphorically drew, and all of this lined up perfectly for life to happen. And yeah. Okay, Mars. Not, I guess, technically it isn't the closest planet to us, but it's the one that we talk about a lot. Anyways, the period of orbit of Mars is 687 days, so nearly 2 years, sort of. It's 1.5 astronomical units from the sun. It's two-thirds the size of Earth. And its temperature ranges from 153 degrees Celsius to 20 degrees Celsius, which is pretty cold, but we still do think of it as a possibility of a place to live. The Mars's core is iron, nickel, and sulfur. The crust is made of iron, potassium, aluminum, and calcium. The Mars has a thinner atmosphere than Earth does. It's made of carbon dioxide, nitrogen, and argon. Argon. But the carbon dioxide part is the important part because it can kind of trap heat in, and that's what keeps it. Because Mars is further away from the sun than Earth. Further away from the sun than Earth is. It still keeps it relatively warm. So the frozen water that we think we found it actually. The frozen water on Mars and the carbon dioxide that we found at the poles in winter is really important. This is why we think Mars might be able to support life. And it also looks bright orange and red in the sky, and it's a little bit above the horizon if you want to try and look for it. Yeah, it's pretty easy to see with your naked eye if the sky is clear. So yeah, I think at the end of this, I said that if you want a homework assignment, you should go out and look for any planets. And I tried to provide descriptions of how you can find them. So I hope you guys do that because it's one of the easiest things you can do in terms of astronomy. Anyways, Mars is one of the most talked about planets. So yeah, pretty important. Jupiter is definitely our biggest planet. And the period of orbit, though, is 12 years, which is crazy. And it's also a lot farther away from the sun than the Earth and Mars are. About 5.2 astronomical units. It's also gigantic. It's 11 times the size of the Earth. It's very cold, negative 145 degrees Celsius. And it's also mostly hydrogen helium. So Jupiter also has this little great red spot that you might have seen, and it's this thing. It looks tiny on the surface of Jupiter, but it's actually bigger than the Earth is. And it's Jupiter is mostly made of hydrogen and helium, like I said, so it's a gas planet, and you see all these little movements in it. These are storm clouds moving around and circulating. Anyways, yes. Jupiter also has 92 moons, and if you want to look for it in the sky, it's very pale. Sorry, I'm just kind of trying to speed through these because it's a little bit late. Sorry. Anyways, Saturn has a period of orbit of 29 years. So I guess it'll orbit 3 times in your life, which is, yeah, okay. Anyways, the distance from the sun is almost 10 times farther away from the sun than the Earth is. It's also about 10 times the size of Earth. So it's roughly the same size as Jupiter. Very cold, once again, because it's very far away from the sun. It's also mostly made of hydrogen and helium. The rings are made of, are made of ice and rock. I was talking about how the Earth at one point had a ring around it, sort of, because of a collision. So this is probably just debris, and also it's debris from collisions that turned it to rock, or is rock, and also froze. So those are what its rings are made of. Saturn also has 145 moons. And it's one of its moons, Titan. I think it's can't quite see it. Read it on here. Oh wait, it's that one. Okay, yeah, that moon, Titan. I thought that was Saturn. Actually, is bigger than Mercury. Is and I made a typo, but it appears to be yellow in the sky, and it's one of the furthest planets that we can actually observe with the naked eye. So yes, this one is also really pretty in some of the recent images that we've captured. Okay, so Uranus, the period of orbit is even crazier. It's 84 years. The distance from the sun is almost 20 times that of the Earth. It's also 4 times the size of Earth, so it's smaller than its counterparts, but or it's smaller than its like counterparts Saturn and Jupiter, but it's still pretty big. Uranus is kind of weird because it's made a lot of water, ammonia, and methane, different chemical compounds, not as much hydrogen, helium. It's considered to be ice, like pretty much frozen. It also has 13 rings, which you might not have known about, but they're there, even though they're pretty faint, and it has 27 moons. So Uranus is a little bit weird compared to its counterparts because it wasn't discovered until 1781 with the use of telescopes and stuff, because you can't really see it with your naked eye. So yes, this one's pretty cold and very far away, and that's why it's cold. But anyways, it's also really pretty. Okay. Neptune. Neptune also has rings, which I don't know. I guess a lot of these planets have rings, and I didn't know about them until like the last few years. Which, yes, its period of orbit is 165 years. So, sadly, I don't think it's going to make a full orbit in any of our lifetimes, but that's okay. It's about 30 times further away from the sun than the Earth is. It's also similar size as Uranus, 4 times the size of the Earth. Very, very cold because of how far away it is from the sun. And it's also mostly made of water, methane, and ammonia. And apparently, it also has a liquid iron core. Like I said, it has 5 rings, 14 moons. We don't really hear as much about these two, like the moons of these two, but they have moons and rings. And this one wasn't discovered until 1846. Once again, wasn't really able to like even be visible to us until we had telescopes. So yeah, sorry, I'm trying to speed through this. But anyways, other objects in our solar system are asteroids. These are basically just rocks left over from the formation of the universe. Like I was saying, there were a bunch of different collisions that happened, and a bunch of debris and rocks were left over. Most of them are in the Kuiper asteroid belt, which is between Mars and Jupiter. If you noticed, Mars and Jupiter have a pretty significant gap between the two of them, and the asteroid belt is in between them. And also the Oort cloud, which is a sphere, not just like a rotating disk, but a sphere surrounding the universe. And it's made of rock and ice because of how far away it is from the sun. But a bunch of asteroids in giant dome around us, basically. And asteroids can interact gravitationally with other objects in the solar system, and they can even collide sometimes. So meteorites, also called shooting stars, basically any matter whatsoever, like it could be rock, could be space debris left by us, that comes into Earth's atmosphere from outer space. So the difference between a meteor and a meteorite, a meteor is anything that enters the atmosphere but doesn't necessarily make it to the ground, and a meteorite is rocks, and this is a picture of one, I think, and other materials that actually do end up hitting the ground. So material like degrades pretty significantly as it's traveling through the atmosphere, even though we can like travel through the atmosphere just fine. When things are like traveling like so fast, they burn up a little bit, and they get significantly smaller, and they form shooting stars. So, sorry, that's why shooting stars have like trails of matter behind them. It's burning up rock, and that's also why many meteors don't become meteorites, because they don't hit the ground. So dwarf planets are any like large objects that can't technically be considered planets, but are still orbiting the sun and are like bigger than asteroids. So in order for a planet to actually be classified as a planet, oh wait, sorry, I just noticed that my camera was off. Oh no, am I glitching out? Okay, wait. Sorry, someone's in the, I just realized someone's in the waiting room and I haven't admitted them. Um, 1 minute. Okay, hi, sorry, I think I glitched out for a minute, but Edwin, I think you just made it in. I'm so sorry I didn't see you in the waiting room until right now, but um, the recording should definitely be up by the time um, I'm done with this. Anyways, I'm gonna finish up the presentation. Dwarf planets are anything that's big enough that we would think of it as a planet, but it doesn't like actually clear its own orbit around the sun. It doesn't clear its own path, and also um, it's not like exactly round. You can kind of see some of these planets like aren't exactly round, and they also sometimes don't have regular orbits. Last part, it's the most important part, but I don't have a lot of time. But we've sent over almost 8,000 satellites into orbit around the Earth. Satellites monitor the Earth's surface, climate, also human activities. They provide internet connection a lot of the time. The International Space Station was a like really big feat that we accomplished. And it's dedicated to researching scientific questions about space. There are a bunch of astronauts up there at any given time, and it's very important. We've also sent 374 like different human launches into space. On April 12th, 1961, the Soviet Union launched the first human into space, which was crazy at the time. That's a little picture of the thing that he went up in, and we will probably continue sending people into space as long as we can, because there's always more to be discovered. And we just did recently. Very cool. Okay. On the form, someone suggested a booklet. I don't know if we have enough time for that. And I also don't quite know how Blicket works, but if you want to try and answer these questions, here are the questions that I did have for you guys. I'm really sorry that we didn't quite have time for this, but I'll try and make another one for next time, and maybe we can do this one first thing next time if we want to have fun, maybe. Oh, also homework that I put down, optional of course, but if the sky is clear where you are, try and go outside and find a planet. Planets are usually the first to appear in the sky because they're closest to us. And you also might want to download an astronomy app. I have a sky guide. I'm not going to get it out right now, but it's really helpful to help you locate things. And it's really interactive and a lot of fun if you want to just try and get out there and do things. So thank you guys. Oh, sorry, I copied this from my old one, but oh yeah, we're learning about how we study the universe next week. So be sure to come back. And also, someone did have I'm gonna stop sharing my screen. Someone did have a question. In what chance do they have of harming us? I'm pretty sure you were talking about the CMEs, and there is a pretty concerningly high probability that they will hit us. However, we can take different like precautions, such as like putting electronics away, covering up any sort of systems, electromagnetic systems that we have, and all of this can like help things out. Okay, so I'm gonna stop the recording